Yeah, so it is started now. Yeah, so we have been talking about this estimation problem. We already have talked about point estimation. Now we'll talk about interval estimation today, and we'll see how far we can go. Today is the last class of this course. Yeah, so to set up the context, so we have a population which we assume that it is large, and then we want to study about certain things about the population. So we assume that there is a random variable x, okay, which gives me the data. So there is a certain measurement, and x will take this corresponding values in the data set. And let's say x has the distribution f of x theta. So we somehow know that what is the distribution that data is sampled from or data is obtained from, but we do not know exactly the value of the parameter theta. So this theta is unknown to us. So for example, suppose a data is generated, a data is given to you, but the way it is produced, or the way the data is produced, you have a guess that this should follow, let's say, standard normal, or let's say just a normal with some parameters, let's say mu and sigma square. Okay. In fact, in general, we have seen that whatever the so this, suppose these are unknown to you, but you at least know that this population data is obtained from a normal distribution. Then the question is now we want to estimate what should be the values of mu and sigma square because they are unknown to us. Now, so how we want to do that? We want to pick a sample out of it. So we cannot deal with the entire data. So we pick a random sample of the objects from the population. And using this random sample or using the sample data, so x1 will be some value, small x1, capital X2 will have some value, small x2, and so on. So basically, we have these values in our hand. Now, using these values, we want to estimate the unknown parameters mu and sigma square. Now, note that even if we do not know, let's say, whether the population data is obtained from normal or not, but when this sample is large, by the central limit theorem, we already know that if n is very, very large, then we can standardize this x bar like the sample mean, and that will follow normal. So that we have seen. Anyway, so we have the sample data x1, x2, small xn, and then we want to estimate the values of the unknown parameters mu and sigma square. And then we discuss different ways to estimate those values mu and sigma square, the unknown parameters associated with the population random variable. Okay, we discuss different techniques to estimate these values mu and sigma square. So this is what is called point estimation because we want to find a value, particular value. And how we did it, we defined something called a statistic. What is that? A statistic is nothing but a function of this x1, x2, xn. So it is just a function, let's say t of this x1, x2, xn. It could be something like a sample mean, sample variance, and so on. And that if you replace this capital X size by the small x size, and if we assume that this statistic, let's say t of this, so estimate, let's say some mu or some sigma square for some different kind of statistics, then we can of course estimate using that statistic for mu and sigma square. And then we said, okay, since we have been talking about point estimation, I mean, we do not know the exact value of mu and sigma. So there, of course, there is a question of accuracy because we do not know how much error it can encounter, how much error there would be, okay, when we estimate this. So instead of the point estimation, then we started talking about what is called interval estimator. So interval estimation, let's say, this is called estimator, by the way. So in fact, if we have mu, we denote it as mu hat, the statistic which will estimate or which will act as an estimator for mu, or denote it as a mu hat, or for sigma square, let's say, yeah, sigma square hat. Now, for the interval estimator or interval estimation of the parameters, let's say mu and sigma, so we want to find an interval where this will lie. Let's say this is some lower bound and this is some upper bound here. So that means I need now two statistics. One is for this one, which we denoted as some L, and this is U. So we need two estimator. One is the lower end and the upper end. Okay. So we want to have mu's to be in the interval with some confidence. Okay, we defined all these terms, but again we said that the way we are devising a method, so that pivotal quantity method, let's say, so here we said, okay, if this fx theta is anything, fx theta is anything, any distribution, okay, we may not have a general way to define what is called the pivotal quantity. And what was this pivotal quantity? Pivotal quantity, so this is the first method which we are talking about finding an interval for the estimation problem. So it's pivotal quantity. So this is again a function. So it is again a random variable, which is a function of this random samples. Because you see, this is x1, x2, xn. These are only known to us. We do not know anything about the population. We only know that population has a distribution and there is certain parameter. Okay, so let's say theta, or there are certain parameters. Okay, which way you want to estimate. Now, what is a pivotal quantity? I said, okay, so this pivotal quantity is a function, okay, of this x1, x2, xn and theta, okay, but its PDF is independent of theta, okay, and we have seen that if this xi's are, let's say, normal, mu sigma square, okay, then we have seen that x bar minus mu by sigma by root n, this is a pivotal quantity of x1, x2, xn. This is a pivotal quantity because its PDF is standard normal, so which is independent of mu, let's say, okay, or it is independent of sigma square. So here we have a pivotal quantity which is a function of xi's and mu, or xi's and sigma, whose PDF is independent of mu or sigma. Now, then we said, okay, this kind of, so for this is very simple, but in general, if we have any kind of a distribution f of x theta, then there is no general procedure to find this pivotal quantity. So then we defined a class of PDFs. In fact, we defined a class of functions, which we called location scale family of functions. Location scale family of functions. And this function we denoted is as f. This is some f x mu sigma. Say mu sigma are any constant. So you can just write mu to be equal to a, sigma equal to b, doesn't matter. But we define this kind of a function, which is 1 by sigma. So sigma, we're assuming that sigma, the constant, is non-zero, x minus mu by sigma, where mu could be anything between minus infinity to infinity, and sigma is positive. So sigma is from 0 to infinity. And I mean, bigger than 0 up to infinity. So in the open interval 0 to infinity, and where G is a PDF. So G is a PDF. So given a PDF, I create another function f. Okay, and I'm saying now if my PDF has this kind of a pattern, like if my given PDF, the population PDF, let's say, if this has, if f of x theta, let's say, if this has this kind of a form for some PDF G, then it would be easier for us to compute the pivotal quantity, and we can estimate theta. Okay. So, for example, I mean, just to have a look, how does this work? Example. See, if we assume that gx to be equal to, let's say, this PDF like standard normal, e to the power minus half x square, then if you define f x mu sigma, okay, then it will be 1 by sigma g of x minus mu by sigma, and then this will be what? 1 by sigma and times g of this, so 1 by root 2 pi e to the power minus half x minus mu by sigma whole square. So this is exactly what is normal mu sigma square. So that's why I denoted it as mu sigma, but you could just write any constant a and b, doesn't matter. So it's not here you see the standard, this general normal distribution is just nothing but a function which is in this class. So this is the class of location scale family. There are two parameters, and mu is called the location parameter. This is the location parameter, and sigma is called the scaling parameter or the scale parameter. Okay, and we can give another example. Let's say, okay, maybe you can just try to find out. Let me just say, because this distribution, this PDF also we talked about in many cases. Let's say this is 1 by theta. Can anybody tell me what is the name of this distribution? let's say 0 less than x less than infinity and 0 otherwise. Can anyone tell me?
Exponential.
Exponential.
Yeah, so this is also in F. Okay, and then my question is, then what is G? For which G, which PDF G, this will be in X, this will be in F in this family. Okay, you can also try to find out. I mean, this is very simple. Okay, you can just check. But I mean, again, so it is just a family. It does not include all possible distribution in this world. For example, I can give you an example of a PDF which is not in this class. So for that kind of a distribution, a density function, it will be hard to find. It will be very hard to find a pivotal quantity. So for example, if you take f of x theta to be equal to theta x to the power theta minus 1, 0 less than x less than 1, and 0 otherwise. Okay, so if you take this PDF, this does not belong to F, meaning there is no G, no PDF G for which this function can be written as this in this particular form, in this particular. So there is no such G available. So that means this is not in this particular class. So what I mean to say is that there are PDFs which are not in this class, and then the question would be, for those PDFs, how to find a pivotal quantity, which we'll not discuss in this course. Now, now I said that it is comparatively or relatively simpler. So let me just make a remark here. It is relatively simpler to find pivotal quantity for PDFs in F. Then the question is, how do we do it? Okay, so what is that? So there are a lot of theorems, but I will not prove all those theorems. But I'll just say what are the, let's say, the estimators. Okay, for the two parameters mu and sigma square or sigma, which are in this family. So given this family, so if your PDF is in this family, then the question will be, what is the estimator for mu and what is the estimator for sigma? Okay, now first of all, if so this is my theorem, but I will not prove it. Okay, so if the PDF, if the density function is in the location family. What is the location family? Location family is, that means now you have to put sigma to be equal to 1. So instead of two parameters, okay, the PDF is such that it is of this particular form, but sigma value is 1. So there is only one parameter here, which is mu, which is unknown parameter, which is mu. Okay, so if then for the question, then the question would be, what is the estimator for mu? Okay, so if it is in the location family, these terms I defined yesterday, so I'm not defining it again. Location family. Okay, so the pivot for the location parameter, for the location parameter mu, because here sigma is taking the value 1, so this will be mu hat minus mu. So this should be a function of x1, x2, xn and mu. So this is mu hat minus mu, where mu hat is the maximum likelihood estimator of mu. Okay, so this is, so directly we know what is the pivot here, or pivotal quantity here. Okay, another is, let's say if my function, okay, let me just write it. So if let me write it like, if sigma dot a is the maximum likelihood estimator of sigma, then the pivot for the scale parameter sigma is sigma hat by sigma. Okay, when the PDF belongs to, so here mu is known, so it belongs to, that means the scale family belongs to the scale family. Okay, and when the when the PDF is in the location family, I know what is the pivot for mu. That means I know pivotal quantity for mu, the unknown parameter mu. When the PDF is in the scale family, then I know what is the pivot, or what is the pivotal quantity for sigma. And if the PDF is in the location scale family, that means in the entire thing, when both mu and sigma are unknown. So if the PDF, a PDF belongs to the location scale family, then the pivot for mu is this: mu hat minus mu by sigma hat, and pivot for sigma is sigma hat by sigma. So anyway, so this is up to some scaling. That means maybe this is not, so this is a statistic after all. We need to know what is the PDF of this, but maybe a scaling of this will be giving you a PDF. So approximately this is the thing, okay? Because we need to know what is the PDF, otherwise we will not be able to solve the problem. Now, what was our original question? I want to find two statistics, okay? And then I can define my confidence interval, and accordingly, we'll have the probability. So now if we just recall what we discussed last day, if Q is a pivot, so recall that Q is a function of Q x1 dot xn and theta, okay, whatever you want to estimate. So if it is a pivot, with 100 times 1 minus alpha confidence interval for theta is what? This is the probability. I have to find A and B such that probability of Q lying between A to B. So if you do not know the PDF of Q, you cannot say this. Okay. So this functions, or this, let's say, statistics. Okay, this one or this one, they have to, this statistic, they have to, follow some standard distribution which you already know. Otherwise, we cannot find this probability. So this should be equal to 1 minus alpha. Okay, and then we can get the interval A and B. Okay, now if I take just simply suppose, so now I have produced some examples for confidence interval. If X is normal, so my PDF is normal with mu and sigma square. Okay, so we know that this is in F, the family, the location scale family. Then what is the pivot for mu? Here I say pivot for mu is equal to mu hat minus mu by sigma hat. Now what was mu hat? For mu hat is what? The estimator for ML, this maximum likelihood estimator, right? Maximum likelihood estimator, MLE, maximum likelihood estimator. Here also sigma hat is, yeah, MLE. Okay. So now what is for the normal? What is mu hat? Can anybody tell me? What is the maximum likelihood estimator for a normal? What is that? Okay, that was X bar. X bar minus mu. Now sigma hat, it was S. If you recall that for normal PDF, the maximum likelihood estimator for mu was X bar, and for sigma it was S. Okay, now so this is the pivot for mu. However, so if we do not know the, let's say, okay, let me make some, instead of going into the general case, suppose if this is in the, suppose mu is known, mu is unknown, let's say, unknown, and sigma is known. Then we just have to make a confidence interval for mu. Okay, so because mu is unknown. So this is my pivotal quantity for mu. Now I want to find a confidence interval with 100 times 1 minus alpha confidence. Now see here, since X is following normal, mu sigma square. Okay, so what is the distribution of this one? What is X bar? X bar is normal. So what is X bar minus mu by S? Yes, I can write it as sigma by root n, or S is known, let's say. So I don't need anything to be done because I assume that S is known, sigma square is known. So what is this? Distribution of this is standard normal, N01. Okay, this is standard normal. So what we can say is the probability. Now see how I am finding the confidence interval. Probability that, okay, I need to define a term. Let me write it down. Alpha, Z alpha, I'll define what is the Z alpha. Let's equal to X bar minus mu by sigma by root n. Let's equal to Z alpha should be equal to 1 minus 2 alpha. Now what is Z alpha here? This is a value, okay? So if you just draw the normal, so let's say this is my normal somewhere, okay? This is my normal with some mean mu, let's say, okay? Then this Z alpha is that value such that in the right hand side, the area is alpha and the left hand side is 1 minus alpha. Okay. Then if, now see here, if this is standard normal, this is standard normal, then it would be line between minus alpha. So minus Z alpha to Z alpha. Okay. So that has to be, probability should be 1 minus 2 alpha, because the right hand side alpha, left hand side it will be alpha. So in between the probability will be 1 minus 2 alpha. Okay. So using this simple calculation, we now have this interval, which is this one. Now from here, what we can say is, if I just do a little bit of calculation, this is mu minus Z alpha sigma by root n, less equal to X bar, less equal to mu plus Z alpha sigma by root n, so which is equal to probability of X bar minus Z alpha by sigma by root n, less equal to mu less equal to X bar plus Z alpha sigma by root n. So what we can say with 100, so this is my confidence interval. So with this confidence, it's 100 times 1 minus 2 alpha % of confidence. Okay, confidence, the confidence interval, the confidence interval for mu is this: X bar minus Z alpha sigma by root n to X bar plus Z alpha sigma by root n. Now I don't want it to be 1 minus 2 alpha, but I want to be equal to 1 by 1 minus alpha. So in that case, what we can do, we can replace the alpha by 2, and that's it. So if the confidence interval, for mu, okay, with interval with 100 times 1 minus alpha percentage of confidence interval, okay, with interval with this confidence, the confidence with what I'm writing. I'm trying to go fast. So the continuous interval. Okay, I will write. So this is the interval. Interval with this confidence. Confidence is this. X bar minus X bar, the value I know because I know X1, X2, Xn. So Z alpha by 2. Z alpha by 2 also I know because it depends on alpha. From the table, I can find out what is the value of alpha. Sigma also I know because I assume that sigma value is known, plus the alpha by 2 sigma by root n. So this is my confidence interval. So I'm done. Now I can do the same thing, okay? When, so here I assumed that the population is normal, okay? It need not be normal, but I am assuming for the timing. I'll do it in general case. And suppose this is known, sigma is known, sigma square is known. Then I have this confidence interval. Now, so this is just a formula then. So if you are asked to find with some, where is the confidence, whatever, the 95% confidence, 90% confidence, then you can find the value of alpha. And using the value of alpha, you can find Z alpha. You know the Z X bar value because you know the sample data. You know sigma because sigma is given. You know n is given. So you can find out the interval. So this is a formula now. Okay. Similarly, next case is assume that X is following normal mu sigma square, and here let's say our earlier I assumed that mu is unknown and sigma is known. Okay, I'm not giving you examples. Okay, so you can just find out the way I said you can find out the values. Okay, now let's say Okay, or I will do it in general. Okay, let me do it in general. Okay, so I can do this also, but let me do it in general because we are running out of time. So assume that x can be any. Okay, now assume that x has, okay, a distribution of x. X has non-normal distribution, non-normal. So the distribution is not normal. Okay. Then the question is, how do I find some, let's say, pivotal quantity? Now, if x is not normal, then using the CLT, using CLT, central limit theorem, what we can say is that x bar minus mu by sigma by root n. This is normal. This is standard normal when n is large. When n is large. So what is the pivotal? See this distribution independent of mu and sigma. So if you want to estimate, let's say mu, okay, and let's say here sigma is given so non-normal and mu is unknown. Mu is unknown and sigma is known. Then I want to estimate. I need to have a confidence interval for mu. So then this is the case. This is normal. Then this is a pivotal quantity for mu. Then using the similar way, what I can say is this is my confidence interval, C alpha by 2. Guys, somebody is knocking my door. Just a minute, I'm coming. Alpha by 2. Okay, so whatever confidence interval we have for the normal, we can do the same thing for not normal. Okay, so when the PDF is not normal, at least when sigma is known, so we can find the pivotal quantity and hence the confidence interval for mu. Okay, using CLT. Okay, now, okay, so yeah. And now see here, okay, let's see here, the problem here is what I'm doing is very simple, but there is a problem here. The problem is I am assuming that mu is known and sigma is not known. Sigma is known, but mu is not known. But this is a typical case. This will not happen in real life. Okay, so it is very unlikely that you will be knowing the variance without knowing the mean, right? Because knowing the variance, you can estimate this mean also. Okay, so this is not realistic. Okay, so we have to find basically confidence interval for population mean when the population variance is unknown. Okay, so then how to do? So this is very simple. Now assume that mu is unknown and sigma square is also unknown. Sigma is also unknown. Okay, and suppose X is normal. So both are unknown. Okay. Then we can have the sample mean like X bar from the sample, and we can also have S square. Okay, the sample variance. Now, what do you know that if this population is normal, the random samples are also normal because Xi's are also having the same distribution as X. So then what you know from our previous theorem that this is following chi-square with n-1 degrees of freedom. This we proved. Okay. And we also know that X bar minus mu by square root of sigma square by n, this is n01. This is normal. So what we can do is now we can define, okay, a quantile, pivotal quantity, let's say q x1 x. If you want to approximate, if I want to estimate, let's say mu, then I can define x bar minus mu by square root of sigma square by n divided by square root of n-1 s square by n-1 sigma square. So which is basically x bar minus mu by square root of a square by n. And this we know, this is the t distribution with n-1 degrees of freedom. So then we can do the same thing. Since we know the pivotal quantity now, this is independent of mu and sigma. Then if I can say the interval with 100 times 1 minus alpha confidence, percentage of confidence, the probability of minus t alpha by 2 n-1 less equal to x bar minus mu by s by root n less equal to t alpha by 2 n-1 degrees of freedom. So if you do the calculation a little bit, so this will be probability of x bar minus s by square root of n t alpha by 2 n-1 less equal to mu less equal to x bar plus s by square root of n t of alpha by 2 n-1. Now say here everything we know, x bar we know because we know the sample data, s we know, n we know. This can be found out from, so depending on what is the confidence you want. So if this, suppose we want to have this interval, this estimation interval or confidence interval with 100 times 1 minus alpha percentage. So suppose it is 90. So I can find out what is the value of alpha. Then n is also given to me. So n-1, I know the degrees of freedom. Then from the table of t distribution, I can find what is the value here. So t alpha by 2 means right hand side, it will be area alpha by 2. So I know this value. So then everything is known, and hence I can find out the confidence interval. So I'm not solving any problem, but anyway, it can be done. Okay. Now, if so, here it is not normal. Here it is normal. Okay. Here mu is unknown, sigma square is also unknown, and x is normal. But again, the same thing. If it is not normal, if x is not normal, if x is not normal, then again we can use what is called CLT, the central limit theorem. And again, we can find out similarly that for n goes to infinity, s square by n will have n01 as n goes to infinity. So, and then the quantile, or the pivotal quantity, the pivot will be, for mu, will be x bar minus mu by square root of s square by n. So this is a function of x1, x2, xn, and mu. And sigma is not needed because sigma is unknown. And here, if I derive, similarly, we can say the confidence interval for this will be this one, because this is normal. Okay, so it will be z alpha by 2, comma x bar plus s by square root of n, z alpha by 2. So this is again a confidence interval for mu. So here we discussed when sigma is known, sigma is not known, normal, not normal, we have a confidence interval. Okay. When sigma is known or sigma is not known, we want to find a confidence interval for mu, the population mean, let's say. Now the same thing we can do for the confidence interval when it is the case for sigma square, the variance. Okay. So the variance, how do you find it? So for the variance, I now need to find out this pivotal quantity. So here, let me discuss what is confidence interval. Confidence interval for sigma square, the variance of the population. Okay. And here the same thing can be done. One is population is normal, population is non-normal, mean is known, mean is unknown. So all four cases can be done. Okay. So first, let's say this thing is normal in mu sigma square. And what I want to find out? I want to find out L and U such that sigma square should satisfy this property with 100 times 1 minus alpha percentage. That is the confidence interval for L. This lower bound is L and upper bound is U. Okay. Now, if we know, suppose mu is known. Suppose mu is known. For the case of normal, let's say mu is known. Then what we can say, we know. So we have to find out a confidence interval for sigma square. Now here, xi is normal. Mu sigma square. Okay. And mu is known. Then xi minus mu by sigma is standard normal. Then xi minus mu by sigma whole square. What is its distribution? If it is standard normal, then square of it. It's the chi square is 1 degrees of freedom. This we proved. And then if we take the sum of it.
Sir. Sir, here mu is the population mean, right?
Yes. Yeah. So I am trying to estimate population mean. Okay. I am not population variance. But mu is known. Mu can be unknown also. We'll do it. We'll deal with it separately. So mu is known. So if I do that, then xi minus mu by sigma whole square, and then if I take a sum, I equal to 1 to n, then we proved it again that it is chi square n. Now see, this is a function. Mu is known, sigma is unknown. So this is q x1 x2 dot 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 xn sigma square. This is a pivotal for sigma square, but its distribution is independent of sigma square. So this can be treated as a pivotal quantity for sigma square now. But if I do that, then what is my how do I find the interval? My definition is 1 minus alpha sub the probability of A, or let's say U, less than equal to Q, less than equal to L, L, and this is U. Okay. So this means probability of A less equal to xi minus mu by sigma whole square over summation. Sum over less equal to U. So if I do that, then this is probability of 1 by A less equal to sum over sigma square by xi minus mu whole square. Okay, I have to take bigger equal to here. 1 by this I'm doing. So bigger equal to 1 by U. Now, if I do that, now I have to keep in the middle sigma square here, and everything I have to spread it out. So if I want to do that, then it will be sum over I equal to 1 to n x minus mu whole square divided by this U will come here less equal to sigma square less equal to, because see it was bigger equal to, I'm multiplying that by less equal to. So this term will appear here. Now this term will go here. So this will be sum over xi minus mu whole square. I'm doing a step jump here, but okay, this is L. So this will be L. Okay, so this is probability of what? Sum over xi minus mu whole square by chi square 1 minus alpha by 2 n less equal to sigma square less equal to sum over xi minus mu whole square by L was chi square by 2 n. that we found out from here. So this is the interval. So this is the confidence interval, sum over I equal to 1 to n xi. The value of xi is known to me, mu is also known to me, by chi square 1 minus alpha by 2 and sum over xi minus mu whole square by chi square alpha by 2 n. So this is the confidence interval. And here everything is known. Everything is known. Right hand side, everything is known. So, so we have the confidence interval for sigma square. So when mu is known, but mu need not be known. Okay. Now this case, when mu is unknown, and of course sigma square is unknown. So now I'm trying to find a confidence interval for sigma square, but I'm assuming that this is normal. Okay, mu sigma square. The distribution is normal. So if the distribution is normal, then what we know from our previous theorem that this is chi square n minus 1. So this implies sum over I equal to 1 to n xi minus x bar square by sigma square is chi square n minus 1. Now everything is known here in this term. Okay, so and this is a function of x1, x2, xn and sigma, this entire function. So this is a quantile, this is a pivotal quantity because if PDF is this, which is independent of sigma. So again, we can write the same thing and we can find out the confidence interval, probability of 1 by chi square alpha by 2 n minus 1 degree of distribution, degrees of freedom, let's equal to 1 by chi square 1 minus alpha by 2 n minus 1. So if I do a little bit of calculation, so if I go to that, then ultimately my confidence interval will be similarly I equal to 1 to n xi minus x bar holds the same thing, just mu will be replaced by x bar because mu is unknown here. So chi square 1 minus alpha by 2 n minus 1 sum over I equal to 1 to n xi minus x bar whole square by chi square alpha by 2 n minus 1. Okay, so when at least normal, we are done. Okay, and mu is known or not known doesn't matter. And similarly, you can find out what happens when it is not normal using. So I'm not doing that. So similar thing, you can do it for not normal case using CLT. Okay, that you can do. So this is the way you can get this confidence interval. Okay. And I also said that we'll discuss about MLE. So the maximum light. Okay, let me do it. Okay, now, so this is one method using the pivotal quantity for the unknown parameter. Now, we can also do using another method, which is, this method is a very simple confidence interval. Okay, for population parameter, let's say population parameters using MLE, maximum likelihood estimation. Okay, so here the simple thing that, okay, we know the problem, we know the context. So here xi is x1, x2, let's say xn, they are the random sample, they have some distribution of this x. And let's say if x has this PDF, x and theta, so we want to estimate theta. We want to find an interval, confidence interval with that confidence, 100 times 1 minus alpha percentage. With this much confidence, we want to estimate this theta. Now here, the first thing to remember is, since this name is matching, maximum likelihood estimator, that means, first of all, we do a point estimation. The idea is, first you find out the theta hat, which is the maximum. So solving that optimization problem, which we discussed yesterday, likelihood estimator for theta. Now, once we do that, then using again the CLT, we can say this minus estimation of expectation of theta hat by square. So this is a statistic, okay? This is giving you a point estimator for theta. So this is a statistic. This is a random variable. So whatever we are writing, we can write that variance of theta hat. And this will follow normal using CLT as n goes to infinity. Variance of this is the variance of the estimator, maximum likelihood estimator of theta. Here the expected value of the maximum likelihood estimator of theta. So we have this as n goes to infinity. And this is here we are done. If this, then according to our definition, 1 minus alpha should be probability of minus z alpha by 2 less than equal to q less equal to z alpha by 2. Now q is here is equal to probability of minus z alpha by 2 less equal to theta hat minus theta by square root of y theta by variance of theta hat. Y theta, can anybody tell me? Less equal to z by alpha by 2. Huh? Think about this. Why I'm writing this as theta? It was expectation of this. Because I'm assuming here again, or this is in general true, that maximum likelihood estimator, okay, for any this thing is what? If you assume, when this is true, that expectation of theta is equal to theta. This was a property of an estimator. Unbiased or biased? Huh? Okay, think about this. It's just a question. We discussed it yesterday. Now, if variance of theta hat is free of theta, then we can have 1 minus alpha is equal to probability of, I can do the little bit of algebra here, theta hat minus z alpha by 2 square root of variance of theta hat less equal to theta less equal to theta hat plus z alpha by 2 square root of variance of theta hat. So this is my confidence interval when this is free for theta. Interval is, this is the lower bound, this is the upper bound. Okay, but in many occasions it may happen that this variation is not free from theta, but it depends on theta. And then we have to use other methods which will not discuss because we don't have time. Okay, now let me say something about quickly about testing of hypothesis. Okay, testing of hypothesis. Hypothesis, what is that? Now see, let me give you an example to understand what we have done and then what is next to be done. So let us set an example. What we have done till now is x1, x2, this is the random sample. And this has the same distribution as x has. Now let us fix a distribution. Suppose the PDF f of x theta is equal to, this is an example, 1 plus theta x to the power theta when 0 is less than x less than 1 and 0 otherwise. So now here you see theta is a parameter which is unknown to us. Now suppose we have a sample. Let's say I have a sample of size 4. Let's say my random sample is like this. X1 is equal to 0.92, x2 is equal to 0.75, x3 is equal to some 0.85, x4 is equal to some 0.8. Suppose this is the sample data which we have. Okay. Now if you recall, what if you want to do point estimation, then first what we have to do, I have to find an estimator for theta. Okay. Now using MLE, if you do it using MLE or maximum likelihood method, let's say LMN, maximum likelihood estimator, I can do the point estimator, and this will be 1 minus, you can do that, 4 by log of x1. In fact, I think we have done this, plus log of x2, log of s3, plus log of x2, x4. So then what I can do, minus 1, then minus 4 by, I put all these values, log of 0.92, plus log of 0.75, plus log of this, plus log of this, x3 and x4. So ultimately we'll get a value. And this value, let us say it is something, okay? This is this value. If we compute this, this will get a value. So this will be a point estimator for theta. That means now here I know theta. Once I know theta, I can put this value of theta from this sample. I can put this value of theta and I know the PDF, which was unknown to me using my point estimator. But I can also do using the pivotal quantity method. Let's say I can do confidence interval. So what will be the confidence interval? This is not normal. If you remember the confidence interval, so using pivotal quantity method, what we are doing is we can find this 1 minus chi square alpha by 2 8 by 2 times sum over. You can find it out and see that this will be the case. This will be the interval minus 1 minus chi square 1 minus alpha by 2, 8 degrees of freedom, and 2 so I equal to 1 to 4 and log of xi. So if you do that, then I know all this xi's. I know the value of this. Okay, I know alpha, whatever the confidence interval. Let's say 90% confidence interval. That means what? 100 times 1 minus alpha is equal to 90. So from here I can find out the value of alpha. Okay, I can find the value of alpha. So if I know the value of alpha, then I can find the value of this from the table of chi square. I know the xi's. So I have an interval for this. So then what we are saying is that with 90% confidence that my PDF is lying. Our PDF is this one, but theta is lying between that interval values, okay, which is with 90% confidence. Okay, so we do not know exactly what is the PDF. We know the form of the PDF and we know the value of the parameter. Now, what is the statistical hypothesis? Let me just define it. What is statistical hypothesis? There are two things. One is, well, let me just define it. What is statistical hypothesis? A statistical hypothesis okay, this is a conjecture. This is a conjecture which you need to prove or disprove. Conjecture, okay, about the distribution of x theta, okay, of the population. About this, okay. The conjecture is usually about the parameter theta if we are dealing with something called parametric statistics. Otherwise, it is about the form of the distribution. So there are two kinds of statistical hypotheses. About theta, about the values of the theta, and about the distribution itself, whether it is true or not. Okay. Now, if the hypothesis, let's say it has x theta, so then okay, let me just define this again. Suppose my hypothesis is H, I denote this conjecture as H. Then I call it simple hypothesis. If this is known, that f x theta is known, this specifies the density function, but theta is unknown. Otherwise, if it is about the distribution itself, then we call it composite hypothesis. So there are two different kinds of hypotheses now. About theta, we are giving it a name. About the distribution, which we are again giving it a name. Okay. Now, in the hypothesis testing, what we want to test, what is the testing here? So hypothesis is a statement about what? Let's say we are talking about simple hypothesis. So about theta. So testing hypothesis means what? This is an hypothesis which needs to be tested, and the hypothesis is called null hypothesis. The hypothesis which is to be tested is called a null hypothesis. The hypothesis which is to be tested is called null hypothesis. Null hypothesis. Okay, these are standard terms. Okay, and the negation of null hypothesis is called alternative hypothesis. The negation of, I'll tell you now what is null hypothesis. Negation of null hypothesis is called alternative hypothesis. Alternative hypothesis. And they use different notation for this. For null hypothesis, they denote it as H naught. For alternative hypothesis, they write HA. Now, what is the hypothesis? What is the statement? What is the null hypothesis? Null hypothesis means nothing but it is a statement that my parameter theta is in certain set. It could be if sigma is this omega 0. Now say you remember omega I denoted as a parametric space or parameter space. Okay, like what are the admissible values of the parameter theta here? Now if this omega 0 is a singleton set, this is point hypothesis that theta is taking that value. If it is interval, then this is a set. So theta is here. Okay, and what is then the alternative hypothesis? Theta is in omega A. So this is another subset such that omega 0 intersection omega A is equal to null set. So if it is here, it is not here. That means omega A must be in the complement of omega 0. And omega 0 union of omega A should be equal to the universal, or maybe the subset of the universal. If it is universal, then it is in the complement. So I need to test this statement, null hypothesis, that whether my theta is in some subset which is to be specified. Now, how it can be specified? It can be specified by many things. Okay. For example, you know the confidence interval. Then you have to test whether it is there or not. Or you are given with any subset. This is any subset. For example, if it is normal, and let's say I want to test whether the mu is in, let's say, -1 to 1. Then this is this. Then my hypothesis is whether mu is here or not. Now, there are different techniques to test whether it is there or not. But there is also a catch that I conclude something because of the test. The test will not get time to do. In fact, we have crossed the time. But let me just define, because you may find it interesting. And if you do a course on statistical inference, then this will be discussed in much more details. But at least you know a brief idea about what is testing, what is the hypothesis. The hypothesis is about the values of the parameter, population parameter. And what is to be tested here? The tested is this statement to be tested whether it is true or false. Now there can be methods to test, but using any method, okay, as I said before, I think yesterday's class, that there are methods, but method can give you wrong answer. And this is the challenging thing. So you have reached to a situation where there are methods, but that may not solve the problem. That may give you a solution which is not correct. Okay, so there is a statement which is H0 is true. So using your test, using your method, you can either say H0 is true, or you can say H0. That means the null hypothesis is not true. That means false. Now, if you say it is true, then you accept that it is correct. So your decision is correct. Correct decision. But if you assume S, okay, and here also it could be reject H0, then that means it is also correct because it is false. Correct decision. Decision. Okay. Decision. But here there is a catch that your hypothesis is true, but the method you have employed, because of that you got something and you rejected. You have rejected H0. That means there is an error in your method, in your testing. This is called type 1 error. And this is called type 2 error. Means you are accepting H0, but H0 is not true. Type 2 error. Okay. Now this testing of hypothesis is all about different methods to test a hypothesis and to come to a conclusion with some probability. Probability of what? Whether H0, the null hypothesis is true or null hypothesis is false. That is all about testing of hypothesis. This is where I'll end. If you have any questions, you can tell me. Just before that, let me tell you the syllabus for the exam. This is very important. Cast test 3 syllabus is up to lecture 19. So we have finished the syllabus for the exam last Monday last week. So this is up to lecture 19. This is syllabus, and this excludes the syllabus for syllabi of class test 1 and class test 2. Okay, so this is the syllabus of this. If you have any questions, you can ask me.